Hello and hi everyone. So today group 1 will be presented about chapter 13 chemical reaction equilibria. So let's get started. So group 1 will be presented about section 13.1, which is the reaction coordinate, 13.2 application of equilibrium criteria to chemical reactions, 13.3 the standard Gibbs energy change and the equilibrium constant. Let's start our presentation with section 13.1, which is the reaction coordinate, will be presented by me, Ida Shariza. So in this section, you will be understand about reaction stoichiometry, equation of mole fraction Yi of the species, and we will take a look at example 13.1 and example 13.2 to how the application of equation of mole fraction in this example, sorry. A general chemical reaction as written in section 4.6 is, let's take a look at equation 13.1, where Vi is a stoichiometric coefficient and Ai stands for a chemical formula. Chemical formula example for H2O, CH4, H2N4, and such else. So the symbol Vi itself, called a stoichiometric number by the sign convention of section 4.6, it is positive for a product, which means at the back of the reaction after the reactant has been react, and the negative for a reactant, which is the reactant that we use in the reaction. To understand a little bit more about what I'm explained just now is, let's take a look at this reaction. For example, CH4 plus H2O becomes CO plus 3H2. So the stoichiometric numbers are for CH4 is -1. Remember what I just told you just now, for the reactant is negative, and same for the H2O is -1 because the mole number for H2O and CH4 is 1. So the stoichiometric numbers are -1. And the products becomes positive. So VCO equals to 1 and VH2 equals to 3. The stoichiometric number for an inert species is 0. So as the reaction represented by equation 13.1 progresses, the changes in the number of mole of species present are in direct proportion to the stoichiometric numbers. Thus, for the preceding reaction, if 0.5 mole of CH4 disappears by reaction, 0.5 mole of H2O also disappears, simultaneously of 0.5 mole of CO and 1.5 mole of H2 are formed. Let's take a look at the differential of amount of reaction. So this principle provides the equations dN2 over V2 equals to dN1 over V1, and dN3 over V1 equals to dN1 over V1, and etc. So the list continues to include all species. Comparison of this equation yields written in the slide. So all terms being equal, they can be identified collectively by a single quantity represent an amount of reaction. Thus, a definition of DE is given by equation 13.2. The equation identified collectively and the general relation connecting the differential change dN1 with DE is therefore becomes dN1 equals to V1 DE. It's actually the number of 1 is I, which is we can substitute the number according to the 1, 2, and continuously, which is in equation 13.3. So the new variable is E, called the reaction coordinate, characterize the extent or degree to which a reaction has taken place. Only changes in reaction coordinate with respect to changes in a mole number are defined by equation 13.3. So the definition of reaction coordinate itself depends for a specific application on setting it equal to 0 for the initial state of the system prior to reaction. Thus, we integrate the equation 13.3 from an initial unrelated state where reaction coordinate, or called E, equals to 0 and Ni equals to Ni naught to a state reached after an arbitrary amount of reaction give the equation in 13.4, which is N1 equals to N1 naught plus V1E. I can be substituted with 1, 2, and continuously number. The summation of over all species yields becomes n summation of Ni equals to summation of Ni naught plus E plus summation of Vi, or in simple equation it becomes n equals to n naught plus Ve. Thus, the mole fraction yi of the species present are related to E by equation 13.5. So this in equation 13.5, we will take a look at example 13.1 and 13.2 to understand how to use in the reaction and to generate the mole fraction of yi of the species present.
So now we move on to the example of reaction coordinate. As for the first example, which is example 13.1, it was given here the equation reaction as for the product CH4 plus H2O equal to the CO2 plus H2. And the question stated, assume there are present initially 2 mole of CH4, 1 mole of H2O, 1 mole of CO2 and 4 mole of H2. Determine the expression for the mole fraction Y initially as function of A. So for the first step, what we're going to do is we have to sum up the stoichiometric coefficient. As we can see for the reaction, from the reaction equation for CH4, the coefficient is 1, and for the H2 also the coefficient is 1. But for the product, the sign for coefficient is negative, and for the reactant, the sign is positive. So we sum up negative 1 plus 1 plus 3 equal to 2. And for the next step is we have to sum up the number of moles of species initially. It was stated here at the equation. For CH4, the number of mole is 2, H2O is 1, CO2 is 1, and H2 is 4. So the total number of mole is 8. And lastly, we have to insert the calculated value inside the formula. This is the formula. So for the Y initially CH4, we insert the number of mole of CH4 2, and we insert the number of coefficient of CH4 1 over the total of number of mole plus total of stoichiometry coefficient, and it apply for the other component also for H2O, CO2 and also H2. So that's it. This is the answer of this example. Now we move on to the second example, which is example 13.2. The reaction was given here. H2O equal to H2 plus oxygen. And the question is find the expression which relate the number of moles and the mole fraction of each chemical species to the reaction coordinate. Consider a vessel which initially contains only number of mole water vapor. So in this question, the step is similar to example 13.1, but the number of moles are not given in this question. So we begin the step with first sum up the stoichiometric coefficient of the reaction. As for the product is -1 and for the reactant is 1 plus 1 over 2. So the answer is equal to 1 over 2. And we insert the calculated coefficient this insert into this formula and we get the answer like this. And for the last fractional decomposition of water vapor, because it's stated at the question, consider a vessel which initially contains only number of mole water vapor, and what we get from the calculated value before for the water vapor H2O, here number of mole equal to A, so insert in this, so what we get is this is the answer.
Hi and Assalamualaikum. My name is Muhammad Azim Firdaus bin Ishaq and I will be presenting about multi-reaction stoichiometry in the chapter 13. So what is multi-reaction stoichiometry? It is when two or more independent reactions proceed simultaneously and the second subscript here indicated by J serves as the reaction index. A separate reaction coordinate EJ then applies to each reaction. The stoichiometric numbers are doubly subscripted to identify their association with both a species and a reaction. Thus, Vij designates the stoichiometric number of species I in reaction J. Because the number of moles of a species and I may change of several reactions, so from the equation 13.3 in the textbooks includes a sum of dni equal to sum of Vij and Dej. So next from the equation, the integration from Ni equals to NiO to arbitrary Ni and Ej gives, and after integration. So for the after integration, you will get this equation. So from the summing of all the species yields, you will get this formula, and for the mole fraction of for the species present in a particular reaction, you will have to use this formula. So next we will be looking at for the examples. So for example 30.3, consider a system in which the following reactions occur. CH4 plus H2O produce CO and 3H2 for the first reaction, and for the second reaction CH4 plus 2H2O produce CO2 and 4H2. So where the number 1 and 2 indicate the value of J and the reaction index. If 2 mole CH4 and 3 mole H2O are initially present, determine the expression for the yi as function of E1 and E2. So from the solution, we can see the stoichiometric number of Vij can be arrayed as follows, like this. And the application from the equation now gives this solution. So now we get the expression for the yi as function of E1 and E2. So that's all from me. Thank you.
Okay, now we move on to the application of equilibrium criteria to chemical reaction. My name is Muhammad Zafrul Hafiz bin Zaili. Criteria of equilibrium. Chemical equilibrium applies to reaction that can occur in both directions. When the net change of the product and reactant is zero, the reaction has reached equilibrium. To determine the state of a reactive system at equilibrium, we need to relate the reaction extent to the total Gibbs energy. The total Gibbs energy of a closed system at constant temperature and pressure must decrease during an irreversible process, and that the condition for equilibrium is reached when the total Gibbs energy attains its minimum value. At this equilibrium state, change in total Gibbs energy equal to zero. Thus, if the mixture of chemical species is not in chemical equilibrium, any reaction that occurs at constant temperature and pressure must lead to a decrease in total Gibbs energy of the system. This can be seen in the schematic diagram of Gt versus epsilon, which characterize the total Gibbs energy and the progress of the reaction respectively. The arrow along the curve indicate the direction of changes in total Gibbs energy at constant temperature and pressure that are possible on account of reaction. The reaction has its equilibrium value, epsilon E, at the minimum of the curve. At this point, G is decreasing and the reaction proceeds in forward direction, while at this point, G is increasing and the reaction proceeds in reverse direction. Meanwhile, at this point, G is not changing. It has reached its lowest point and there is no net change in the reaction. Thus, the equilibrium criteria are when the total Gibbs energy is a minimum and its differential is zero. That's all from me. Thank you.
Hi, my name is Norfarhani Metizaidi and my metric number is 192599. Today I want to present about the standard Gibbs energy change and the equilibrium constant. So the standard Gibbs energy is the free energy change for a process at 298 Kelvin and at 1 atm pressure in which the reactant in their standard state and converted to products. So the difference between this Gibbs energy and the standard one is the free energy depend on the concentration of the reactant and products, while for the standard Gibbs energy, it's just the same as Gibbs energy, except for the reactant and products are in their standard state. So, the standard Gibbs energy change. Basically, the equation is delta G equals to delta G naught plus RT ln Q. So, at equilibrium, this delta G will equals to 0 and this Q, which is a reactant quotient, will equals to K, the equilibrium constant. So when we want to rearrange it, it becomes like this: delta G equals to 0, delta G naught plus RT ln K. So it will become like this. So right now we want to manipulate it, this expression. So by dividing delta G naught with RP, and we will get the ln K. Or we can also manipulate it to get the ln K. K equals to exponential negative G negative delta G naught over RT. So we're gonna take a look at the relationship between the standard Gibbs energy change and the equilibrium constant. The solubility product constant K of lead to iodide is 1.4 times 10 to the power of negative 8 at 25 degrees C. Calculate delta G naught for the dissociation of lead to iodide in water. So the equation, this is the equation given. So the equation wants the delta G naught. Okay, as we know, the equation is delta G naught equals to negative RT ln K. Negative R is the gas constant, which is 8.314 joule per kilomole, and T is the temperature, which we in Kelvin. So, and ln K 1.4 times 0 times 10 to the power of 8 negative 8. So negative 8.314 times 25 plus 278 times ln 1.4. Okay, basically we get 44,804.92 joule per mole. In this case, we need to change the unit to kilojoule. So it's gonna be 44.804 kilojoule per mole. So this answer, so this question really describes the relationship between the delta G naught and the K. As the K is lower than 1, so the delta G will be greater than 0. This is the last value, and so when delta G when K is small, the delta G naught will be a large value. So for this situation, we can call the reaction as the non-spontaneous reaction. When it comes to the other situation, when K is equals K is bigger than 1, so the delta G will automatically smaller than 0. So this situation we will call as a spontaneous reaction. So this is how the standard Gibbs energy change relates with the equilibrium constant. So that's all for me. Thank you.
Hi, my name is Siti Hajar binti Azaman and my metric number is 193250. My part is to explain about the standard Gibbs energy change and equilibrium constant. Okay, for this part, the equation used is D Ng equals to Nv dp minus Ns dt plus summation of mu I dni. So, if changes in the mole numbers Ni occur as a result of a single chemical reaction in a closed system, then each dni may be replaced by the product Bi d epsilon. Then it becomes d Ng equals to Nv dp minus Ns dt plus summation of V I mu I d epsilon. Because Ng is a state function. The right side of this equation is an exact differential expression. Then the quantity mu I Vi mu I represents in general the rate of change of total Gibbs energy of system with respect to the reaction coordinate at constant T and P, but this quantity is zero at the equilibrium state. Then what is K? In spite of its dependence on temperature, K is called the equilibrium constant for the reaction. Summation of I, Vi, Gi represented by delta G0 is called the standard Gibbs energy change of reaction. So the equation that used for this part is K is identically equal to ESP negative delta G over RT. Then whenever it modified, it become ln K equals to negative delta G over RT. And then we use for the next question is delta G equals to negative RT ln K. Okay, let's look at the 3 example questions.
Okay, for the example questions, we need to remember to use these equations, which is delta G equals to delta G0 plus RT ln Q. But whenever it's at equilibrium, Q equals to K and delta G equals to 0. Okay, so then when we insert the equilibrium state equations, we get the 0 equals to delta G0 plus RT ln K. So this the equation we must remember to use to all the questions that ask for equilibrium constant. So first question is calculate the equilibrium constant for the following reaction at 298 K. So this is the reaction N2 plus 3H2 equal becoming to 2NH3 and Gibbs energy at negative 3.0 kilojoule. Use the equation like above. Delta G0 equals to negative RT ln K. Insert all the number that should put in the equation. And then use the calculator because it's easier to use the calculator straight away. Okay, just put the values, and then we got 608,950.233 joule. Change to kilojoule. It's easier to see. So the calculation is when delta G0 less than 0, K bigger than 1, equilibrium mixture contains more product than reactant. Okay, for the next question, just the same question, which is asking for the equilibrium constant but using the different temperature 464 Kelvin. Use the same reaction as well, but delta G0 is equal to 0,
So that means it's at equilibrium. So just use the same equations but put the zero, and whenever the zero, ln K must be equal to 0 because the mass. So the K equals to 1. Whenever delta G 0 equals equals to 0, K must be 1. So at equilibrium, the mixture and the reactant, the mixture of the product and the reactants is favored. It's the same. So the same question, last question, same question which is asking for the equilibrium constant but at temperature 1000 Kelvin with the same reaction as well, but with different delta G0 is equals to 106.5 kilojoule using the same equations. And remember to put the equation in the SI units, which is joules, not kilojoule. And the same as the first question, using the calculator straight away because it's easier like this. Then we got K equals to 2.734 multiply 10 power of negative 6. Okay, whenever delta G0 more than 0, K lower than 1, so the equilibrium mixture contains more reactants than products. So whenever we want to do this kind of question or this kind of parts, remember that whenever delta G lower than 0, reactions is spontaneous. Whenever delta G more than 0, reaction is non-spontaneous. And lastly, whenever G equals to 0, reaction is at equilibrium. Thank you for watching our video.